All right, today we're putting on our detective hats. We're diving into the world of logarithmic equations, and our mission, should we choose to accept it, is to hunt down the real answers and expose any imposters that might be hiding in plain sight.
I love this quote from our source material because it just sets the stage so perfectly. You know, in most of math, algebra is our best friend, right? It's the tool we trust. But when logarithms get involved, sometimes it can mislead us. It can create these false leads that look like the real deal but are actually dead ends.
So that's the big question, isn't it? How do we tell the difference? We need a solid method, a kind of detective's code that lets us separate the real solutions from the fakes. And luckily for us, there's one fundamental clue that never, ever lies.
And here it is. This is the unbreakable rule. It's the bedrock of our whole investigation. The thing inside the logarithm's parentheses, its argument, it has to be a positive number. Not zero, not negative, always positive. This rule right here, this is our lie detector test for every single potential solution we find.
Okay, so every good detective needs a reliable set of tools. And for solving these log equations, our toolkit is a pretty standard 4-step procedure. Let's open it up and see what we're working with.
So here's the plan. Step 1, we get the log all by itself on one side. Step 2, we use its inverse, an exponent, to basically bust the variable out of that logarithm. Step 3, we just do the normal algebra to solve for x. And then step 4, this is the most critical step of all. We check our work. And this isn't just about catching typos, it's a mandatory part of the investigation to unmask those imposters.
All right, let's get our hands dirty. We'll start with our first case file. This one should be pretty straightforward. A perfect chance to see how our toolkit works in the field. Okay, here's our equation. The natural log of the quantity 2x minus 1 equals 3. Now notice the log is already isolated, so step 1 is already done for us. We can jump right into the action.
So we exponentiate both sides using base e to cancel out that natural log. That leaves us with a much friendlier looking 2x minus 1 equals z cubed. A little bit of simple algebra gets us our answer. X is about 10.54. But we're not done. Now for that crucial check. We plug 10.54 back into that original argument, 2x minus 1, and what do we get? We get about 20. And since 20 is definitely greater than 0, our rule is satisfied.
So our suspect checks out, it's a valid solution, case closed. A nice clean one to get us started. But you know, they're not always this easy. Okay, let's move on to our second case file. This one's a little more involved, and I've got a feeling we're about to meet one of those imposters we've been warned about.
Here's the new case. Log base 2 of x plus log base 2 of x minus 2 equals 3. The first thing you should notice is, this time we've got two different log terms to deal with.
So our first move is to condense the evidence. Using the product rule for logs, we can combine those two terms into a single logarithm. Next, we exponentiate to break that variable free. That gets us to a quadratic equation, and when we solve it, well, we don't just find one answer, we find two suspects.
So, the algebra has pointed us to two potential culprits, x equals 4 and x equals negative 2. One of these might be legit, and the other could be the imposter. It is time to bring them both in for questioning. Let's interrogate x equals 4 first. We plug it back into the original equation. Log base 2 of 4? Yep, that's fine. Log base 2 of 4 minus 2? Well, that's log of 2. Also fine. Both inputs are positive. Verdict? X equals 4 is a valid solution. Okay, now for suspect number 2, x equals negative 2. The moment we plug it into that first term, log base 2 of negative 2, alarm bells should be going off. That violates our unbreakable rule. So x equals negative 2, it's the imposter. Case closed. So this raises a really big question. If negative 2 was never a real solution to begin with, why did our algebra give it to us? I mean, where do these fakes, these so-called extraneous solutions, even come from? Well, it all happens back in step 2. See, when we exponentiate, we're actually changing the fundamental nature of the equation. We're leaving the restricted world of logarithms and entering the wide-open world of polynomials. And that process can take a ghost solution, one that was never valid in the first place, and make it look like a perfectly real, tangible number.
Our source material puts it pretty dramatically. It says it's not enough to just identify these ghost solutions. You have to exercise them. You have to cast them out by checking them against that original domain.
And that brings us to the detective's code. These are the rules to live by. First, checking your answers is not optional. It is a mandatory, required part of the logic.
Second, you have to plug your solutions back into the original equation before you changed anything. And finally, you throw out any solution that breaks our unbreakable rule. No exceptions.
Now you might be sitting there thinking, okay, this is a neat little math puzzle, but I promise you, these detective skills have some seriously profound real-world consequences. This isn't just about finding x, it's about solving real problems.
Take a look at this number. Just 7.4. What on earth could that possibly have to do with any of this?
Well, that is the average pH of human blood, a super delicate balance that is absolutely essential for us to live. And pH itself is defined by a logarithmic equation. When a biochemist needs to figure out the concentration of hydrogen ions to keep that pH stable, they are literally solving a log equation.
This is something scientists do every single day to understand everything from our health to the chemistry of the environment. The exact same detective skills you're learning right now are the skills they use to decode the chemical language of life itself. The logic is the same, whether you're in a Precalculus class or a state-of-the-art lab.
It really makes you wonder, doesn't it? Math isn't just a bunch of formulas to memorize. It's this whole landscape of rules and logic, and yeah, it's filled with these hidden truths and even the occasional imposter. So the real question is, what other secrets are out there, just waiting for a good detective like you to find them?